Arizona, July 1980. Under the relentless, punishing sun of the Sonoran Desert, the mercury had pushed past 120 degrees Fahrenheit. Outside, the air was so blistering, it felt like standing in front of an open blast furnace. Asphalt on Route 89 was turning to black tar. Air conditioning compressors across Pima County were blowing out one by one, and power grids were buckling under unprecedented demand. Inside conventional suburban homes, families were trapped in sweltering 95-degree living rooms, watching their drywall swell and their electric meters spin out of control. But 3 miles outside of Marana, sitting completely off the grid, on a sun-scorched plot of dusty red wash, stood a home that looked like nothing the local building inspector had ever seen. Or rather, it didn't stand at all. From the dirt track, all you could see were 2 heavy copper ventilation hoods sticking out of a low, planted mound of desert brush, and a heavy oak door embedded straight into the side of an earth berm. Inside that home, without a single solar panel running, without a generator humming, and without a single ton of mechanical air conditioning, the indoor thermometer hung at a rock-steady, bone-cool 65 degrees Fahrenheit. Let that sink in. While the ambient outside temperature was hot enough to bake bread on the hood of a pickup truck inside, Arthur Vance was wearing a flannel shirt, pouring hot coffee, and living in total, silent thermal equilibrium. 2 years earlier, when Arthur first brought a heavy backhoe onto this flat, sun-bleached acreage and began digging a trench 12 feet deep into the rock-hard desert caliche, his neighbors thought he was losing his mind. They called it Arthur's Hole. Local contractors shook their heads and warned him he was building a subterranean coffin, a damp, dark pit that would either cave in under the weight of the earth or suffocate anyone inside during the summer heat waves. They were wrong, because what Arthur understood, and what modern housing developments had completely forgotten, was an ancient law of thermodynamics written into the very crust of the earth. Before you build your next home, or before you trust your survival to a fragile electric grid, you need to understand the structural, atmospheric, and thermal principles that allowed one man to outsmart the harshest desert on the continent. If you value forgotten American engineering and real-world off-grid survival wisdom, hit the subscribe button right now and leave a comment below telling us the hottest temperature you have ever experienced in your hometown. Now, picture this. It was 1977. The United States was gripped by the tail end of the 70s energy crisis. Rolling blackouts had already exposed the extreme vulnerability of modern American home design. For nearly 3 decades, homebuilders across the Sun Belt had been erecting thousands of thin-framed, drywall and fiberglass tract houses. These homes were essentially giant glass and plywood ovens, constructed with zero thermal mass, reliant entirely on massive 5-ton electric air conditioners to force the internal environment into livability. If the power cut out for even 4 hours during an Arizona summer, those houses turned into dangerous heat traps, rising to over 100 degrees inside in less than 90 minutes. Arthur Vance was a retired civil engineer who had spent 25 years analyzing structural stress and thermal transfer for industrial infrastructure. He looked at the sprawling developments popping up around Tucson and saw a disaster waiting to happen. He knew that sticking a 3-inch layer of fiberglass insulation inside a 2x4 wooden wall was nothing more than a temporary bandage. Heat is not a force you can simply block with a thin blanket. Heat is energy in transit and in the desert. Radiant energy from the sun hits a rooftop with the force of over 300 British thermal units per square foot every single hour. Eventually, that heat bleeds through. It warms the shingles. It saturates the plywood decking. It cooks the attic space up to 160 degrees Fahrenheit, and then it radiates down through the ceiling drywall into your living room. No matter how hard your air conditioner works, it is fighting a losing war against the relentless mass of the sky. Arthur decided he would not fight the sky. He would let the earth take the blow instead. He bought 40 acres of cheap, remote desert land north of Tucson, an area dominated by saguaro cactus, creosote bushes, and soil so hard it could shatter a steel shovel. His plan was radical, yet ancient. He would not build a house on the desert. He would integrate his home into the desert. He was going to build an earth-integrated, subterranean vaulted residence, buried beneath 6 feet of dense, compacted desert soil. When he applied for his initial building permits in Pima County, the zoning officials stared at his blueprints in utter disbelief. The plans didn't show a standard pitch roof. They didn't show double-hung windows. They showed a heavy parabolic arch constructed from steel-reinforced concrete, topped with multiple layers of elastomeric waterproofing, bentonite clay, and 600 tons of raw earth. The building inspector literally flagged the file and wrote across the cover sheet, "Unconventional design. High risk of structural failure and inadequate ventilation." The local builders in the area were even more vocal. A nearby rancher pulled his truck up to the edge of Arthur's excavation site, looked down into the massive 12-foot deep pit, and laughed out loud. He told Arthur, "You're digging yourself a cave, old man. Come July, that hole is going to turn into a steam cooker. You'll bake alive in your own dirt." Here's what everyone missed. The rancher and the building inspector were thinking about earth-sheltered homes through the lens of standard construction. They assumed that because the desert surface hits 140 degrees Fahrenheit under the midday sun, the dirt underground must be just as hot. The numbers don't lie. The top 3 inches of soil do indeed absorb massive surface heat. At 6 inches down, the temperature fluctuations begin to flatten. By the time you reach 8 to 10 feet beneath the surface, something extraordinary happens. You hit the Earth's thermal equilibrium zone. At that depth, the soil is completely shielded from daily solar radiation. Instead of experiencing wild temperature swings between 80 degrees at night and 120 degrees during the day, the deep Earth acts as a massive thermal flywheel. It doesn't respond to hours of heat. It responds to months. In fact, at a depth of 10 feet in southern Arizona, the ground temperature remains at a constant, stable 63 to 67 degrees Fahrenheit all year round. Think about that for a second. While the surface world above is experiencing lethal desert heat waves or freezing winter nights, 10 feet below, the Earth maintains a permanent, natural climate zone that never changes. Arthur wasn't trying to invent a new air conditioning system. He was simply moving his living space into a zone where air conditioning was physically unnecessary. Stay with me here, because burying a home underground sounds simple on paper, but in practice, it is one of the most dangerous structural engineering challenges a builder can undertake. If you build an underground house incorrectly, 2 things will happen, and both of them can be fatal. First, the massive weight of the soil above will slowly crush your roof. 6 feet of dry desert soil exerts a vertical load of roughly 600 to 700 pounds per square foot. Add a sudden desert monsoon downpour that saturates the soil with water, and that weight doubles to over 1,400 pounds per square foot. A standard flat timber or light steel roof will bow, crack, and catastrophically collapse under that kind of overburden. Second, if you seal a house completely underground without proper passive air exchange, you create a toxic, stagnant environment. Human respiration produces carbon dioxide and moisture. Cooking with propane or lighting a wood stove produces deadly carbon monoxide. And deep soil naturally off-gases trace amounts of radon. Without powered electric fans, an underground house can quickly become an oxygen-deprived trap. Arthur knew he couldn't rely on electric fans. If the grid failed, his ventilation system had to work purely on the laws of physics, completely unpowered, completely automatic, 24 hours a day. He spent 6 months perfecting 2 key engineering systems before he poured a single yard of concrete. First, the structural shell. To handle 600 tons of soil without thick, prohibitively expensive steel I-beams, Arthur chose the strongest structural shape known to architectural history, the parabolic arch. Instead of flat walls and a horizontal ceiling, Arthur designed a continuous curved vault, 24 feet wide, 12 feet high, and 60 feet long. When weight is placed on top of a parabolic arch, the downward force does not bend the material. Instead, the gravitational load is transferred laterally, down through the curved sides of the concrete wall, and pushed directly into the unyielding earth footings on either side. The heavier the soil load on top, the tighter the concrete arch locks into compression. To construct it, Arthur poured a heavy, 3-foot wide by 2-foot deep concrete footing along both edges of his excavated pit, reinforced with thick, 5/8-inch steel rebar. Then, he erected a temporary timber framework, bent heavy steel mesh across the curve, and tied in a grid of continuous rebar, spaced just 6 inches apart. He didn't use standard truck-mixed concrete poured into forms. To ensure maximum density and zero air pockets, Arthur hired a specialized crew to spray pneumatically applied concrete, known as shotcrete, directly over the rebar grid at high velocity. He built up the shell, layer by layer, until the concrete arch was a solid, seamless 8 inches thick. There were no joints, no seams, no roof nails, and no rafters. It was a monolithic concrete monolith, custom-built to withstand the weight of a mountain. And that's when everything changed. When the shotcrete cured after 28 days, Arthur had created a bomb-proof underground vault. But now he faced his second and most crucial hurdle: waterproofing and passive air circulation. In the desert, monsoon season brings sudden, torrential flash floods. If rain penetrated his earthen cover, water would seep through microcracks in the concrete, creating toxic mold and ruining his interior. Furthermore, he needed a way to pull fresh, cool outdoor air into the home and force hot, stale air out without using a single watt of power. For waterproofing, Arthur rejected cheap plastic sheeting that would degrade over time. Instead, he applied a thick coat of asphaltic emulsion over the entire outer concrete dome, followed by a layer of bentonite clay, waterproofing membrane. Bentonite clay is a remarkable natural mineral. When dry, it forms a tough barrier, but when exposed to moisture, the clay expands up to 15 times its original volume, creating an impermeable, self-healing gel seal that locks out water completely, even if the concrete shell developed a hairline settling crack. The expanding bentonite clay above it would automatically swell into the gap and block any water from entering. Over the clay membrane, Arthur installed a heavy-duty, dimpled drainage mat, which directed any percolating rainwater away from the crown of the vault and down into a perimeter French drain filled with crushed river rock. With the structure fully sealed and waterproofed, Arthur turned to his most brilliant achievement, the dual conduit passive cooling and ventilation system. This is the exact physics mechanism that allowed his home to maintain 65 degrees Fahrenheit, even when the desert outside hit 120 degrees. To understand how Arthur cooled his home without electricity, you have to understand the stack effect, also known as thermal siphon ventilation. Hot air is less dense than cool air. Therefore, hot air naturally rises, creating a zone of low pressure below it. Arthur realized he could use this natural pressure differential to create a continuous, self-powering air pump. At the highest point of his concrete vault, right in the center of his living ceiling, Arthur installed a heavy, 12-inch diameter insulated solar chimney stack. This steel pipe extended straight up through the 6 feet of earth soil and extended 4 feet above the surface of the desert mound. The exterior of this protruding chimney was painted flat black and covered with a clear glass cylinder, creating a mini solar heat collector at the top of the pipe. When the desert sun beat down on that black pipe, the air inside the top of the chimney heated up rapidly, rising to over 140 degrees Fahrenheit. As that air superheated, it expanded violently and rushed out the top of the vent into the open desert atmosphere. This rapid upward exhaust created a continuous, powerful vacuum at the ceiling level inside Arthur's underground house. To replace that exhaust air, the vacuum needed a source of incoming intake air. If Arthur had simply opened a window or a roof vent, it would have sucked in the blistering 120-degree outside air from the desert surface, ruining his cooling strategy. So, Arthur didn't draw air from the surface. Instead, he buried two separate 100-foot-long, 10-inch diameter corrugated galvanized steel pipes deep in the ground beneath his home, 6 feet below the basement floor level. These were his subterranean cool tubes. The intake ends of these long pipes emerged far away from the house, hidden under the dense shade of an overhanging mesquite thicket on the north side of his property, where surface temperatures were significantly lower. As the solar chimney on his roof exhausted hot air out the top, the resulting internal vacuum forced fresh outdoor air into the remote intake pipes. As that warm outside air traveled through 100 feet of dark, subterranean steel pipe buried 10 feet underground, it underwent rapid thermal exchange. The massive, 65-degree thermal mass of the surrounding Earth absorbed the heat from the incoming air continuously. By the time the air completed its 100-foot journey through the subterranean cool tubes and spilled into Arthur's living room floor vents, its temperature had dropped from 120 degrees down to an astounding 66 degrees Fahrenheit. No moving parts, no electric motors, no refrigerants, no power bills. The hotter the sun baked the solar chimney on top of his mound, the faster the air rose inside the pipe, and the faster cool, earth-chilled air was drawn into his living quarters. It was a completely self-regulating system. The hotter the desert got outside, the harder the passive ventilation system pumped cool air inside. When Arthur finally backfilled 6 feet of excavated earth back over the waterproofing membrane and planted native drought-tolerant desert flora across the mound, his house literally disappeared into the landscape. From a distance, it looked like a natural hill rise in the desert wash, while his neighbors were finishing their standard wood frame houses nearby, installing massive propane tanks and hooking up heavy electrical meters. Arthur was putting the final touches on his interior. He built heavy, custom oak cabinetry, installed a small wood-burning stove for the rare winter freezes, and fitted a dedicated exterior air intake pipe directly into the firebox, ensuring the stove would never consume interior oxygen. He hung a large brass thermometer on his solid concrete interior wall, right next to his subterranean air vents. Then came the true test, the summer of 1980, a year that would go down in regional weather history as one of the most brutal, unrelenting heat waves ever recorded in the American Southwest. COE, voiceover audio text. By mid-June of 1980, a massive high-pressure heat dome parked itself directly over the American Southwest, trapping millions of tons of dry, stagnant air across the Sonoran Desert. Day after day, the sun rose like a ball of molten brass into a cloudless sky. The surface temperatures were staggering. In Tucson, official weather stations registered 114 degrees Fahrenheit, then 116, and by early July, localized ground surface readings pushed past 122 degrees Fahrenheit. On the asphalt highways, truck tires were delaminating from the sheer heat of the roadbed. In suburban neighborhoods across Pima County, residential central air conditioners were running at maximum capacity, 18 to 20 hours a day without stopping. And then, the inevitable happened. Under the relentless, continuous electrical load, suburban transformers began overheating and exploding along the county lines. Substations buckled. Power grids collapsed into rolling brownouts, leaving entire subdivisions without electricity for 24, 36, and in some areas, 48 hours straight. Think about that for a second. In a standard American tract house built out of 2x4 timber framing and fiberglass insulation, when the air conditioning turns off in 120-degree desert heat, the home becomes unlivable. In less than 2 hours, the attic space heats up to 160 degrees. That heat saturates the ceiling drywall and radiates straight down into bedrooms and kitchens. Inside those homes, tap water coming out of the cold pipe was scalding warm. Interior walls were warm to the touch, and families were forced to sleep on concrete patio floors wrapped in damp towels, suffering from early stages of heat exhaustion. Hank, the local cattle rancher who had stood at the edge of Arthur's excavation pit 3 years earlier and called his design a subterranean coffin, lived just half a mile down the wash. Hank's modern, 3,000-square-foot wood-framed ranch home was equipped with 2 massive, 5-ton electric cooling units. On the third afternoon of the major power outage, the temperature inside Hank's living room reached 105 degrees Fahrenheit. His wife was sick. His dog was lying motionless on the tile floor, and his electric generator had seized after 18 hours of continuous strain. Desperate for help, Hank pulled his pickup truck onto Arthur's property. When Hank stepped out of his truck, the radiant heat coming off the bare desert earth was so intense it burned his throat with every breath. The landscape looked scorched, dead, and lifeless. All that was visible of Arthur's homestead was the low, earth-covered mound, thick with thriving native desert vegetation, and those 2 copper vent hoods extending into the sky. Hank walked up to the heavy oak door, embedded into the side of the earth berm, and knocked. Arthur opened the door, and that's when everything changed. As the door swung open, a gentle, steady breeze of cool, dry air flowed out into Hank's face. It wasn't the artificial, icy draft of a struggling compressor. It was fresh, crisp, odorless cool air, like stepping into a subterranean limestone cavern on a spring morning. Hank stepped across the threshold and closed the door behind him. The deafening roar of the desert heat, the blinding white sunlight, the waves of shimmering thermal haze instantly vanished into total, peaceful silence. Arthur wasn't sweating. He wasn't wearing a tank top. He was wearing jeans, leather boots, and a light cotton long-sleeve shirt. Hank looked up at the brass thermometer mounted on the 8-inch thick solid concrete wall near the center of the vaulted vault. The needle rested precisely at 66 degrees Fahrenheit. Let that sink in. Outside, 6 feet above their heads, the desert surface was blistering under 120 degrees of heat. Inside, without power, without a generator, without a single drop of fuel or moving mechanical parts, the air was 54 degrees cooler than the sky. Hank stood there in complete silence for a moment, ran his hand along the cool concrete wall, and whispered flatly, "How is this possible?" Arthur pulled up a wooden chair for his neighbor, poured him a cold glass of well water, and walked him through the exact mechanical physics of what was happening around them. Here's what everyone missed. Most people assume that an earth-sheltered home works simply because dirt is a good insulator. That is completely incorrect. Dirt is actually a terrible insulator when compared to modern synthetic materials. Fiberglass insulation traps air. Polystyrene foam stops heat transfer. Earth, on the other hand, has low thermal resistance. Dirt does not stop heat. Earth absorbs heat. What Arthur utilized was not thermal insulation, but thermal mass and thermal inertia. Soil has a high heat capacity, meaning it takes a vast amount of thermal energy to raise the temperature of a cubic yard of earth by just 1 degree. Because Arthur had buried his arch beneath 6 feet of dense, compacted desert soil, and set his floor slab 8 feet beneath the natural grade, his house was enveloped by thousands of tons of dense earth mass. When the blazing sun hits the surface of the mound in June, the heat begins to travel downward through the earth. But heat does not move through solid soil quickly. It moves at a snail's pace, roughly 1 inch every 24 hours. This phenomenon is known as thermal lag, or the thermal flywheel effect. To move through 6 to 8 feet of packed earth, it takes thermal energy roughly 5 to 6 months. Think about what that means in practice. The extreme summer heat hitting the top of Arthur's earth mound in July 1980 wouldn't actually reach his concrete interior roof until December. By the time that summer thermal wave finally arrived 6 months later in winter, the outside surface air would be 40 degrees, and that delayed heat wave would gently warm his home during the cold desert nights. Conversely, the deep, freezing ground temperatures of January were reaching his concrete vault in the middle of July. Arthur was literally living in the coolness of last winter's climate, shifted 6 months through the crust of the Earth. The Earth was acting as a massive, natural thermal battery, storing winter cold for summer use, and summer heat for winter comfort. Stay with me here, because thermal mass alone is only half the equation. If you simply bury a box underground and rely on thermal mass, you will solve the temperature problem, but you will create a lethal air quality crisis. This is where the majority of DIY earth-sheltered builders make fatal design mistakes. In an underground space, moisture from human breath and cooking builds up rapidly, leading to black mold, condensation, and oxygen depletion. If you burn propane, wood, or gas inside a sealed subterranean structure without engineered ventilation, carbon monoxide will settle into the lower breathing zone, creating a deadly trap. Hank looked around the ceiling, expecting to hear electric exhaust fans. But all he heard was the soft, rhythmic hiss of air entering through floor vents. Arthur took Hank over to his kitchen and pointed out the 3 critical components of his passive safety architecture. First, the dedicated combustion intake. Arthur pointed to his small, iron wood-burning stove. In a standard house, a stove draws room air into its firebox, burns the oxygen, and sends smoke up the chimney, creating negative air pressure that pulls cold or hot drafty air into the house through door cracks. In a subterranean home, a stove drawing room air can quickly starve the occupants of oxygen. Arthur had installed an isolated, 3-inch steel air pipe running directly from the exterior ground surface, straight through the earth mound, and sealed directly into the bottom of the stove's firebox. The stove drew 100% of its combustion oxygen directly from outside, completely isolated from the interior atmosphere of the living space. When Arthur lit a fire in winter, 0 indoor oxygen was consumed, and 0 toxic carbon monoxide could ever backdraft into the room. Second, the passive air exchange rate. Arthur showed Hank his solar chimney stack. By painting the top portion of the steel exhaust pipe black and encasing it in clear glass on top of the mound, the air inside that vertical pipe heated up to over 140 degrees whenever the sun was out. As that hot air rose rapidly out the top vent, it created a continuous, steady vacuum. That vacuum pulled fresh air through his 2 long subterranean intake pipes. Arthur had calculated the exact diameter of those tubes. Each tube was 10 inches wide and 100 feet long, buried 8 feet below ground, where the earth temperature was 63 degrees. As hot, dry outdoor air was pulled into the remote intake openings far away in the mesquite shade, it was forced to travel through 200 feet of cool underground steel piping. The velocity was tuned so that the air had a residence time of nearly 8 seconds inside the buried pipe. During those 8 seconds, the hot air transferred its thermal energy into the surrounding earth through conductive pipe walls. The air entered the pipe at 120 degrees Fahrenheit and entered Arthur's living room floor at 66 degrees Fahrenheit. More importantly, this passive thermosiphon was moving over 300 cubic feet of fresh air into the house every single minute. That meant the entire air volume of Arthur's living space was completely refreshed, filtered, and exchanged every 45 minutes. Without consuming a single watt of electricity, there was no stagnant air, no accumulation of radon gas, no buildup of moisture, and 0 carbon monoxide risk. The numbers don't lie. While the electric grid in Pima County was completely dark, and families across the valley were battling heat exhaustion in 95-degree indoor living rooms, Arthur's passive system was pumping thousands of cubic feet of cooled air into his subterranean home using nothing more than solar radiation, gravity, and conductive earth mass. Hank sat at Arthur's wooden table, sipping his cold water, watching the brass thermometer stay glued to 66 degrees. His perception of off-grid engineering had been completely shattered. What he had once mocked as an insane hole in the ground was, in reality, the most sophisticated, self-sustaining, and thermally stable residence in the entire state of Arizona. Hank looked up at Arthur and said, "My wife can't stay in our house another hour. She's getting heat sickness. Can I bring her and our dogs down here until the power comes back on?" Arthur smiled, opened his pantry, and pulled out extra wooden folding chairs. "Bring them over," Arthur said. "There's plenty of cold air for everyone." Over the next 4 days of the historic 1980 heat wave, Arthur's subterranean home became an oasis for 3 neighboring families. Children slept comfortably on rugs on the concrete floor. Food stayed fresh, and while the world above ground was buckling under extreme climate stress, inside the Earth Vault, life went on in absolute comfort. When the county power grid was finally restored 5 days later, the regional power company reported over $3 million in transformer damage and thousands of ruined appliances. Many homeowners in the valley were hit with electric bills exceeding $400 for a single month, an astronomical sum in 1980 just from their air conditioners trying and failing to keep up with the heat. Arthur's electric bill for that entire month, $0. And that was only the beginning of the story. Because 2 months later, in late August of 1980, the Sonoran Desert was struck by the second extreme environmental hazard of the region. The summer monsoons arrived. In less than 3 hours, a massive convective thunderstorm dumped over 4 inches of torrential rain onto the sun-baked, unabsorbing desert soil around Marana. Now, picture this. The desert earth in southern Arizona is notorious for its impermeability. Decades of intense solar heat bake the top layer of soil into a concrete-like crust called caliche. When torrential monsoon storms roll in over the mountains, the baked soil cannot absorb the sudden volume of water. Instead of soaking into the ground, millions of gallons of rainwater collect into violent surface torrents, rushing through dry washes and spilling over roads in matters of minutes. In late August of 1980, a wall of dark, purple thunderstorm clouds swept across Pima County. In less than 3 hours, over 4 inches of water poured out of the sky onto the dry soil around Arthur's property. Dry creek beds instantly turned into roaring rivers of brown water, carrying mud, rocks, and uprooted desert brush down the valley. At Hank's ranch, surface water collected against the foundation of his wood-framed home, seeping under door frames and flooding his garage with 3 inches of muddy runoff. Hank, terrified that Arthur's subterranean home would be transformed into an underground swimming pool, pulled on his raincoat and drove his tractor down the muddy wash to check on his neighbor. When Hank arrived at Arthur's property, he saw a scene that defied every instinct about earth-sheltered building. While surface water was rushing across the surrounding flatland, Arthur's underground home was standing dry and completely undisturbed. Here's what everyone missed. Subterranean building is not just about digging a pit and throwing dirt over a roof. It is an intricate game of hydrological engineering. Arthur had designed his surface topography long before the first drop of rain ever fell. First, the land contouring. Arthur had not buried his home in a depression. He had chosen a slight, natural elevation rise on his 40-acre tract. Around the base of his buried earth mound, Arthur had excavated wide, shallow diversion swales, lined with large river rocks and native vegetation. These swales acted as hydraulic bypass channels. When the torrents of surface water rushed down from the upper desert slope, they hit Arthur's stone-lined channels and were directed cleanly around both sides of his earth mound, guiding the floodwaters safely away into a lower wash 50 yards downstream. Second, the hydrostatic pressure mitigation layer. Water that did land directly on top of Arthur's planted earth mound slowly percolated down through the 6 feet of soil. If that water had hit a flat, concrete ceiling, the hydrostatic pressure would have built up rapidly, forcing water through microscopic pores in the concrete. But Arthur had engineered a multi-tiered drainage shell over his concrete vault. Directly above his asphaltic coating, he had installed a continuous layer of high-density, dimpled drainage matting, covered by a thick bed of washed river gravel. When water filtered down through 6 feet of dirt, it struck the dimpled mat and was instantly funneled sideways down the curved slope of the parabolic arch. It never sat on top of the concrete. It flowed freely down the outer curve of the dome and dropped directly into a deep, continuous French drain system, running along the perimeter footings 8 feet below grade. That perimeter drain, constructed from perforated corrugated pipe, buried in crushed gravel, carried the water away from the foundation and discharged it into an underground dry well far away from the living quarters. And what about moisture entering the living space? Arthur's bentonite clay membrane performed exactly as nature intended. As the percolating rainwater touched the buried layer of bentonite, the clay particles absorbed the water and swelled into a dense, impermeable, waterproof barrier, sealing the outer concrete vault tighter than a submarine hull. Hank walked down the concrete entry steps into Arthur's home, expecting to smell damp earth or see water leaking through the ceiling. Instead, he stepped into an environment that was bone dry. The interior humidity hung at a comfortable 35%. The smooth, painted concrete walls showed zero signs of dampness, zero water spots, and zero structural weeping. The solar chimney stack on top of the mound was still drawing fresh air, and the subterranean cooled tubes were operating flawlessly. Hank stood inside that quiet, dry space while thunder echoed across the desert sky above, and realized that Arthur had solved two of the most destructive forces in desert architecture: extreme heat and catastrophic surface flooding. Think about that for a second. In a single summer, Arthur Vance's off-grid subterranean home had survived a 122-degree thermal heat wave that paralyzed the regional power grid, and a 4-inch monsoon deluge that flooded standard surface homes across the county. And it had done so without consuming a single kilowatt of electricity, without burning a gallon of fuel, and without requiring a single repair. The numbers don't lie. Over the next 2 years, word of Arthur's achievement spread among structural engineers, off-grid builders, and regional architects. University research teams from Tucson installed remote temperature and humidity sensors throughout Arthur's Earth Arch to monitor its performance over a full 12-month cycle. The empirical data collected from those sensors was undeniable. During the winter months, when ambient desert night temperatures dropped to a freezing 28 degrees Fahrenheit, the lowest temperature ever recorded inside Arthur's living room was 63 degrees Fahrenheit. A small fire in his ironwood stove for 20 minutes in the evening would raise the temperature to 71 degrees, and that heat was absorbed and held by the massive concrete walls for over 24 hours. During the summer months, when surface temperatures routinely exceeded 115 degrees, the highest temperature recorded inside the home was 68 degrees Fahrenheit. His annual energy expenditure for heating and cooling was absolute zero. His long-term maintenance costs were virtually non-existent. There were no roof shingles to replace after windstorms, no exterior timber siding to paint or seal against solar degradation, no gutters to clear, and no mechanical air conditioning compressors to repair or replace every 10 years. The Earth was protecting the structure from the elements, and the structure was serving its occupants in total thermal stability. And that's when everything changed. Hank, the skeptic neighbor who had spent years doubting the project, sold a portion of his cattle herd in 1982, brought in an excavator, and hired Arthur to design an earth-sheltered addition for his own ranch homestead. Local contractors, who had once dismissed Arthur's design as a subterranean trap, began studying his blueprints for parabolic shotcrete vaulting and subterranean cooled tube thermal exchange. They realized that Arthur hadn't built a primitive cave. He had created a masterpiece of passive, thermodynamic architecture. Stay with me here, because the lessons learned from Arthur Vance's desert homestead go far beyond historical curiosity. They represent a fundamental blueprint for human resilience in an era of increasing grid fragility. Today, millions of modern homes remain completely dependent on complex, vulnerable electrical infrastructure. A single ice storm, a solar flare, a cyber attack on regional utility networks, or a prolonged heat wave can instantly cut off mechanical climate control for millions of people. When the power grid fails, a standard modern home becomes an uninhabitable shell in a matter of hours. Yet, directly beneath our feet, the Earth offers a permanent, reliable, and completely free thermal sanctuary that never fluctuates, never fails, and never requires a utility bill. By understanding the simple, unyielding laws of physics, thermal mass, soil thermal inertia, parabolic compression, and solar thermosiphon ventilation, human beings can build shelters that do not fight nature, but work in complete harmony with it. Arthur Vance lived in his subterranean desert homestead for over 30 years, in total comfort, complete independence, and absolute peace. He proved that true survival wisdom is not about hoarding canned goods or buying expensive machines. It is about understanding how the natural world works and building your life on principles that cannot be disrupted by a power outage. If you found value in this deep dive into historical survival architecture and off-grid engineering, hit the like button, subscribe to our channel, and share this video with someone who values self-reliance and real-world independence. Before attempting any earth-sheltered construction, remember that subterranean building requires professional structural engineering calculations, local soil density tests, proper excavation safety protocols, and strict adherence to active and passive ventilation safety standards. Never burn fuel in an enclosed space without dedicated, isolated fresh air intakes and verified exhaust systems. Until next time, stay prepared, stay grounded, and keep building for resilience.